I am Parth Patra from IIIT Karnool. I am currently a second year student of the CSE department, and today I am presenting my project, Semantic Segmentation of the Land Cover AI dataset. Land Cover AI dataset is basically orthophotos of European region, and orthophotos here as satellite images. For further details about the Land Cover AI dataset, this is what it is. So it covers land cover from Poland and Central Europe. These are all RGB satellite images. There are 33 satellite images which have 9000 cross 9000 pixels, and 8 satellite images which are 4000 cross 4500 pixels. This covers an area of 216.27 kilometers square. Now these are very large images, so to feed them into our network, we'll have to split them into 512 cross 512 pixels first. Now coming to what segmentation is. So basically the image here is what we get fed into our network. This is a satellite image of what Europe looks like from the sky. Now our task is to produce the gray and white image there. So basically we try to split what trees are, what the coast is, what roads are, what the buildings are, and stuff like that. So that is the task that we have today. Now there are many approaches to segmentation. I will be using the unit variation. Unit is basically an encoder, a bottleneck, and a decoder, which helps to predict this right here. So we provide this image right here with a mask that we define over this image, which is used to predict that. Now, unit normally gives you a IOU score of around 60%, but to improve on this IOU score, we use the attention mechanism that is nowadays being used in transformers. So basically what attention does is it provides you details on what is the important part in this image. So basically if we look at the trees, the attention mechanism would tell us, okay, there's a cluster of trees right here, so you pay attention to this area right here to try to find the trees. There's no point trying to find trees right here when we already are being told that this is a coastal area. So this is what an attention block does to your unit. Now about IOU, how we measure how good this result is. So this is what IOU is. It's a lot like what we do in DLD. So this is the total area that we have, and that there is the area of overlap. So given our mask, we find how much of our prediction is overlapping with the given mask. That is our numerator, and the total area is given as a denominator. Using this, we find the ratio which calculates our IOU percentage. Now the final output of this model here, which is a custom model developed by me, gives around 76%, and the normal unit architectures give around 60 to 65%. Now moving on to my approach for this. So again, these are the dataset details that we're playing with right here. There's it's RGB maps, which are very large. So we split them into 512 cross 512 pixels, and that is what we're doing right here. So we split the image mask tiles into size of 512 cross 512 pixels. Yeah. So next step is obviously to prevent overfitting. We try to provide some augmentation onto the data. So I've used many augmentation steps. One is random rotate 50% of the images. Basically, if the image is still, we try to rotate it to find if it will be a perfect overlap or not. Next, we try a horizontal flip, which completely flips the image horizontally to make sure, again, that we'll be able to predict where the trees and stuff are. Hue saturation changes the colors and stuff like that. Randomized brightness, it changes the brightness of the image on a whole to make sure that where the sun is falling doesn't help predict where any particular data is. Then we divide ours into train and test splits as we usually do. It is an 80-20 split. We have around 10,000 images, and we use an 80-20 split to generate a train set of 8,000 images and a test set of 2,000 images. Now, our model, it's a custom model which is developed on the basis of a unit. A unit again has an encoder, a bottleneck. A bottleneck is usually just a convolution block, but here we have used the pyramid Boolean net layer from the PSP2 architecture in the bottleneck. So this is a more detailed view of our architecture. So here we feed the image. Again, as I told you, the original images were around 9000 cross 9000 pixels. We broke them down into 512 cross 512 pixels, generating a total set of 10,000 images from the initial 90 or 100 images that we were given. So this is a predefined ResNet block. ResNet is a very well-known architecture. We use this encoder and only the encoder here. All the gray blocks here are feature maps that are provided along the way. And now, this pyramid pooling module is what we use as a bottleneck here. This is actually derived from the PSP2Net architecture. It is also very commonly used in the YOLO architecture. So we use that as a bottleneck here. And here it's all the upsampling being done. The orange arrows are upsampling, which again increases the size of the image. And the red arrows right there are the convolutions that we do. Again, as you can see here, this is the legend of what is being done. So here, as I mentioned the attention blocks earlier, the attention blocks are directly connected to the outputs of the feature maps from the ResNet encoder. There are 3 locations, and all 3 of these are finally summed. The attention from all 3 of these feature maps are finally summed when we are getting your final output. Now, this is the pyramid pooling architecture that we have used, again, derived from the PSP2Net architecture. You can look at it how this helps right here. So it produces images of the exact same size in terms of pixels, only the number of channels is what changes. And that is the job of the bottleneck. Here, we again define the augmentations in the code. It's the exact same as what I mentioned earlier. The 90 degrees rotations, horizontal flips, random cropping, hue saturation value, it changes the saturation of the RGB values, and random brightness, it changes the brightness of the images at random. Now, here I create the datasets, which is the train test clip. Yes, this includes both the image, which is the RGB image, and the mask that we provide to the network. Here we create data loaders from the dataset, and again, our train test split 8,000 images and 2,000 images in the train and test set respectively. Now, this is what the images look like. So, let's say trees are being represented in yellow, maybe grasslands in green, and bare lands in purple. Now, this is the exact same architecture that I mentioned earlier. It's this architecture right here. So, this is the attention block, the one in green. This is the con, the arrow in red. This is the upper con, which is the orange arrow, which increases the size. This is the pyramid pooling layer, which is completely derived from the PSP.NET. And this is the actual encoder and decoder that we have used. Here, this is a basic overview of the attention unit model that we've used. Now, coming to our results, we have trained this using the cross entropy loss because there are multiple categories, and we have used the optimizer, which is the Adam optimizer. We have used a learning rate of 10 power minus 5, and we have trained it for around 8.5 hours. That is because the size of the image and the quality of the image is so high that it takes a lot more time than normal to train. Again, these were broken down from 9,000 across 9,000, which is why it explains the 8.5 hours which it took to train. This is all been trained on Kaggle using their Tesla processing unit. Now, we use many final metrics to calculate how good our values were. So here you can see, for each and every class that we have, we got a IOU as I mentioned earlier, for background, building, woodland, water, and roads. So this led to an average IOU of 0.76, which is very good compared to the IOU that you achieve from the normal unit. Now we further achieved a precision score, which tells you how precise your image is compared to the mask of 0.88, which is 88%, and the F1 score, which is normally used to tell how good a segmentation model is of 88%. These are very good compared to the numbers that we had from the regular unit. Now these are some of the results that we got. We can compare them to the ground truth. This was the input and the mask that we provided, and that was the prediction that the model made. So obviously there are a few flaws here and there, but we come to what a few limitations that we had. So why is it imperfect? Why are there still a few flaws here and there? So as you see here, this was the split of the images that we received. So if you look, this is in 10 to the power 5, the bar graph here. So that is the scale of the bar graph. So you see, we barely have any building images, but we have a lot of background or a lot of woodland images. So what this leads to is everything, even the building pixels would be classified into background or woodland pixels. So while segmenting, this would provide a very big fault. So we tried a lot of measures to prevent this. One very good measure that we thought of was providing weights in the cross entropy loss. So what this would do is we would provide a lot of weight, basically inversely proportional to the number of building images that we had. This would make sure that it paid a lot of attention to the building pixels. Yet this did not really provide a very good result as much as we were expecting. It led to a 71% ILU, which is still less than the 76% that we had. Another method that we thought was we artificially populate the number of building images or the building pixels that we have. We could use GANs, we could use other adversarial networks to help increase the number of images or the number of pixels here, but yet that did not lead to a very good score. And yeah, for further references, you can look at the landcover.ai dataset. This is the dataset that we used, and also any other GitHub sources which you find. Thank you.